Okay, today we're going to go through the second part of the acid-base, second week of acid-base. And I'm going to start out by reading or going through the answers to number 70. Number 70 is the first problem that you have to work. So over here, although it says 79, this is the same problem. It says determine whether aqueous solutions of the following salts are acid, base, or neutral. And it all depends on the kinds of ions that are formed by these salts. For example, this first one dissociates into iron plus 3 and chloride. Iron plus 3, as it states here, is an acidic metallic cation. Chloride, on the other hand, is a conjugate base for a strong acid. The conjugate base is neutral. The aqueous solution is therefore acidic because you have an acidic metal ion in the conjugate base for a strong acid. The next one, potassium carbonate, dissociates into potassium, which is a neutral cation, and the carbonate ion. Carbonate ion is a conjugate base for a weak acid. You could look this up in the appendix under weak acids and bases. And this is a weak acid and therefore is basic. And the aqueous solution is therefore basic. The ammonium bromide dissociates into ammonium, which is a weak acid, and bromine, which is a conjugate base for a strong acid and is essentially neutral. Therefore, the aqueous solution is acidic. The last one, potassium chromate, dissociates into potassium, which is a neutral, and chlorate, which is the conjugate base for a strong acid and is therefore also neutral. So neutral plus neutral means that it's going to be a neutral solution. So that's number 70. Number 73, because I was asked a question about number 73, I've already done number 73. Let's get rid of this. I've already done number 73, so I'm not going to do that again. The next one, I believe, is 76. Let me make sure. Yes, 76. So let's take a look at number 76. It states the ion HTE minus is a amphiprotic species. It can react as either an acid or base. That's what amphiprotic means. It means that it can accept a hydrogen ion or it can discharge its second hydrogen ion. What is the Ka for an acid reaction of HTE with water? So first of all, HTE plus H2O would go to form Te minus 2 plus H3O plus. So that's what this means when it says, what is the Ka for an acid reaction? An acid reaction of this would mean that it donates this proton to this species right here. What is the Ka for this? Ka, 2, which is what this is equal to the products divided by the reactants. And if we look at this table right here, it's going to be 1.6 times 10 to the minus 11. So Ka2 is equal to 1.6 times 10 to the minus 11. The next question is, what is the Kb for the reaction in which this forms a base or functions as a base? So in this case, goes to form, if it functions as a base, it accepts a proton from the water, and you have this. So this is going to be the same as, if you look at the backwards reaction, the same as 1 over the Ka1, okay? In other words, this is going to write out as H2Te OH minus to HTE minus, which is going to be the same as 1 over the Ka1. Ka1 is equal to 2.3 times 10 to the minus 3. It's actually not 1 over the Ka1, it's the Ka of water over the Ka1. And so if we put the Kb here, will equal 1 times 10 to the minus 14 divided by 2.3 times 10 to the minus 3. This is going to equal 4.35 times 10 to the minus 10. The third question here is demonstrate whether or not the second ionization of Te2 can be neglected in the calculation of Te is equal to 1.0 molar solution of Te, H2Te. My feeling about that is when you have a number like this that you can neglect, that the effect of that on the overall reaction. So I would say yes, you can neglect that. Moving on to the next week, we have 80, 84, and 90. Number 80 says, what is the H3 or the hydrogen ion concentration in a solution of 0.25 molar, that's acetic acid, plus 0.03 molar sodium acetate? So what we have here is acetic acid plus water goes to form H3O plus acetate ion. And we have the concentration here is 0.25. Concentration here is 0.03. If we draw our little ice diagram, the starting concentration is 0.25 and 0 and 0.03. This is C2H3 here. This is H3O. And this is HC2H3O2. And the change here is minus X plus X plus X. So this is going to be X, and this is going to be 0.03 plus X. And this is going to be 0.25 minus X. And so Ka is equal to X times 0.03 minus or plus X divided by 0.25 minus X. And on the bottom here, we can ignore this because X is going to be substantially less than 0.25. We can do the same thing on the top here because and end up with 0.303, excuse me, times x is equal to 0.25, which is equal to Ka. And the Ka is 1.8 times 10 to the minus 5 is equal to 25 over 0.03x. If you do the math here to find x is 1.5 times 10 to the minus 4, which is the hydrogen ion concentration. And you can see that subtracting this from this number or adding it to this number will have no effect on either of those numbers. So your assumption is accurate. The next problem is problem number 84. What is the effect of the concentration of acetic acid, hydronium ion, and acetate ion when each of the following is added to a buffer solution of equal concentration of acetic acid and sodium acetate? All right, we need to write this down. First of all, we're starting with a buffer solution where it's an acetic acid acetate buffer, and this is what happens in this solution. So this is the buffer solution, and you have a certain amount here and a certain amount here, okay? Which is not unlike the previous problem we just did here, okay? And the question is, what happens to the various concentrations when you add these certain things? What happens to the acetic acid concentration? What happens to the hydronium ion concentration? And what happens to the acetate ion concentration? So if we add HCl, that's a strong acid. So we're going to add HCl here, which adds hydronium ion here. Will shift everything this way so that this increases. And because this has to be consumed in order to do this, this will decrease. And depending on how much of this is added, this will be consumed by the shift, but most likely this will be increased because you're adding acid to this. If you add acetate, which is what this is, then you're increasing this. This will shift this way, so you're going to decrease this and increase this. This is all the Chatelier's principle. If you do C, you're adding sodium chloride. Now, sodium chloride, the reason they're mentioning it is because it's sodium acetate. But in this situation, the addition of sodium chloride has no effect. OH, what happens with OH? Well, OH will react with this to produce water. So this is going to go down, and this is going to go up. Okay? But the effect of water, when you write those concentrations, is not taken into account. So when this goes down, the shift is this way. So this will go up, and this will go down. This is D, by the way. C was no effect. And then lastly, they ask if you add more acetic acid, which is this has to go up. This will shift it this way, so this goes up and this goes up. Now, how much this goes up depends on how much you add, because it could end up being neutral or even leading to a mild decrease. Okay, so let's look at the next one, which I think is 86. '86 said, what will the pH of a buffer solution prepared with 0.2 molar ammonium and 0.4 molar ammonium nitrate, and just enough water to give 1 liter of solution. Okay. So you can look at it this way. And say that it forms a base. Now it's also possible to look at it the other way, but in general we look at it this way. The Kb for this is written like this. And so we have ammonium ions times the concentration of hydroxide ion divided by concentration of ammonia. The Kb in this situation is 1.8 times 10 to the minus 5. You can look that up in the back of the book. I just happen to know that. And so now we do our ice table again. And so we start out with 0.2 of ammonia, 0.4 of ammonium ion, and no hydroxide ion. We're going to add a hydroxide. We're going to add to this, and we're going to subtract from this. So this is going to be 0.2 minus x. This is going to be 0.24 plus x, and this is going to be x. And then we put these in here. So first of all, on the top we have 0.4 plus x times x divided by 0.2 minus x. And again, we can make the assumption that neither of these is going to be big enough to change this. So 1.8 times 10 to the minus 5 is equal to 0.4x divided by 0.2. Now we can change this and just call this 2x is 1.8 times 10 to the minus 5, right? Because 0.2 into 0.4 is 2. And then we divide both sides by 2. This divided by 2 is now going to be 9 times 10 to the minus 6. And that is the hydroxide ion concentration. Now at this point, now the question was, what is the pH? Now at this point you can do one of two things. You can calculate the pOH and subtract that from 14, or you can use the water equilibrium equation to calculate the hydrogen ion concentration. For me, I think it's easier to basically find the pOH first. And if we do that, the pOH here is going to be 5, the pOH is going to be 5.05. So the pH is going to be 14 minus 5.05, which is going to be 8.95.